All right, so today we're going to review the assignment. So get out the assignment. Those the identifying the acids and bases. We're going to do some notes. Show you how to use your calculators with logarithms and calculations. I know it's been a while, but we're going to do logarithms in a very different way than what you guys do in math. Still same rules, but different. And then I'm going to let you loose on the assignments. Okay? Okay, so here are the answers for 1 through 6. Take a look at those. Do you guys have any questions on them? Now, the thing I want to point out on these is that, for the most part, these are going to be kind of your net ionic equations. Now, we'll look at net ionic equations here in a second and revise them a little bit. But in these equations, you can see we've got charges on stuff. You need to make sure that if those charges are there, that you write them correctly. So a good example of this is this one here. Both of these are charged to begin with. We're taking a hydrogen away from this ammonium, because it's acting as the acid, and it's going onto the hydroxide. Our charges must be balanced then. So if we have a hydrogen, which is a +1, going on to that hydroxide, you're going to get water neutral. Because this ammonium has lost NH+, the hydrogen ion, it's going to end up being neutral. The key is that the total charges, so your total for the charges up here as on the reactant side, has to be the same as the total charges of these on the product side. So if we add these up, +1 and -1, we get 0. Over here, 0 plus 0 is 0. So when you have your equations written out and balanced, they need to balance, equal on opposite sides. So in this reaction here, we've got one hydrogen, move that over a little bit. We've got one hydrogen going from the sulfuric acid to the phosphate. That's why this is the acid, this is the base. Is there any way that this could be an acid? Why? You said no, Ella. Why? Speak loudly so the other classes can hear you. I can't even hear you. Aren't you in choir?
Yeah.
Aren't you loud? Project.
She's very loud.
From the diaphragm. What's the definition of an acid? Somebody, what's the definition of an acid? Gives a hydrogen away. Can that be an acid?
No.
Why?
No hydrogen.
Okay, there we go. Okay, so this has to be the base, right? Now, look at the charges. We have 0 charge for this, and we got 3 negative for this. The total over here is 3 negative. Once this loses a hydrogen, it's going to become a 2 negative. I'm sorry, a 1 negative, and then this is going to gain a hydrogen. It's going to become a 2 positive, but our total over here is still going to be what? 3 negative. Okay? Does anybody have any questions on those? Does anybody have any questions on these? Okay, let's move on. Oh, did I make a mistake? Which one? 11?
Yeah. NH3. And
Oh.
NH4.
Okay, so I just completely. Because of my answer, or confused in how to do it? Well, that's because I did one. So, HPO4 2 minus plus NH3. They're telling you that HPO4 is the acid, it's the acid column. So it's going to end up being PO4 3 minus plus NH4 because the ammonia was acting as the base. Okay, so let's do some net ionic equations because there's a slight change to how we do net ionic equations now. Okay, so when we're doing net ionic equations, going back, so how we've done it up to this point, what split? Aqueous things that were soluble. So we use solubility rules. We look at the reactions. If something was soluble, then we split it apart. We called those things that were soluble aqueous, correct? Yeah. Now, last lecture, we talked about electrolytes. And we said that we can have things that are going to be aqueous that are not going to split apart or split apart to a very tiny extent. So for our purposes, what we are going to do now, and this is why you need to know your strong acids and bases. But I'll go ahead and say it now. Quiz next time. Yeah, quiz next time.
Is it just
And doing this. Okay. So if you can do the homework that we just went over, you know, your strong acids and bases. You'll probably throw a couple problems on pH on there just to round it out. We'll cover that today. It's easy. Okay? But the primary thing is going to be the acids and bases, and we'll do some net ionic equations. Now, so our change is that non-electrolytes and weak electrolytes they don't get split. They are aqueous, but don't split. Now, the importance of knowing the strong acids and strong bases is so that we know what to split and what not to split. So in our chemical equations now, if we have a strong acid or a strong base, yeah, that's going to get split apart. But if we have a weak acid or a weak base, yeah, it's going to be aqueous, but we are not going to split it apart. So again, memorize your 6 strong acids. Memorize a group 1 and 2 on the periodic table if they're hydroxides or strong bases, and you don't have to worry about it. So, if I had HCl, hydrochloric acid, what kind of acid is it? Strong acid. And I put it in water. It's going to react to give up the hydrogen. On the product side, what am I going to get? I'm going to start calling cards, but I can't wait. Know your cards, so when I call it, you can go right away. We don't have time. 5 of clubs.
You get H3O and Cl2.
No, not Cl2.
Cl
Cl.
minus.
There you go. Now, strong or weak? This is aqueous. Strong or weak? Split or no? Yes, because it's strong. Strongs get split. Weaks and nons don't. So we would say H plus, Cl minus. H2O is what? Liquid. Split or no?
No.
Never have. Never will. Now, this is where things get a little bit different. If they have a charge on them, they do not get split apart. They already are split apart. Okay? So if it has a charge, no splits. So this would be kind of our complete ionic equation. If you can go from the net ionic from the equation, the overall equation, straight to what I'm going to do last here is the net, I'm fine with that. I'm not going to ask you to write this out. Some of you did, some on the test. I'm fine with that. I'm not going to ask for it. But if that helps you get from this to the net ionic equation, go ahead and do it. What cancels? Chlorides. So our net ionic equation is simply that. Okay? Do this. You got a minute. No guarantee. Queen of diamonds. Connor, go. Don't complain about it, just do it.
NO3 plus
Hydroxide?
Yeah.
OH minus?
Yeah.
So both of these are giving up a hydrogen and 2 hydrogens are disappearing?
No. H3.
Just H3O? And NO3? Yeah. Okay, that's the reaction. Strong or weak, class?
Strong.
Split?
Yeah.
So somebody tell me what the net equation is going to be right now? Nikos, go ahead and tell me. You shook your head that? Yes.
H plus H2O equals H3O plus.
I'll fill in for people that are wondering how, again, it's how we get from here to here. If this splits apart, we're going to get the hydrogen, we're going to get the nitrate, we have our water. This is splitting apart because it's a strong acid. Not splitting apart because we've never split apart water. It's going to produce the nitrate because this is an acid. It's going to give up the hydrogen. The water's acting as the base. That gives us our hydronium. That's what this is called. I think that's what you had that, but you were calling it hydroxide, right? Okay. So this is called hydronium. The nitrates cancel. That gives us this. Everybody okay? Who's got questions? You got a minute, go. Is that you, Mia? Let's go.
H3O3 minus, and then plus H3O plus.
Can you tell me what the net ionic equation is going to be?
Is it just that or everything's split apart?
It is just this. Because what is this? It's a weak acid. It's not on our list of 6. It's why you need to know your list of 6. So you can look at it and say, oh, that's a weak acid. I'm not going to do anything to it. This is the net ionic equation. Okay? So you can get an idea here that if it's a strong acid, you're going to have a net ionic equation or a strong base. You're going to have a net ionic equation you're going to deal with. If there is a strong acid or strong base anywhere in the equation on the reactant side, we're not going to see them on the product side. You have a net ionic equation you're going to make. If everything's weak or water, you don't. The equation you write out is the net ionic equation, like this one. Okay? Go. You got 30 seconds. 2 diamonds.
H3O plus NO2 minus.
What's the net?
Is that?
Why?
Because that's a strong acid.
HNO3 is, HNO2 is not. Again, know your 6. Okay? So this is the net ionic equation for this reaction. Now switch over to a base. Acids are pretty easy to identify. There's not very many weak bases that I can use with you guys for you guys to recognize them as weak bases. So most of the time I would say this compound acts as a base. If it starts H something or another, pretty much that's an acid. Anybody remember what we called this? Ammonia. That I am going to ask you to know. Just know ammonia, NH3. You see that? It's the base. You got 30 seconds. All right, who's got it?
NH4 plus OH minus.
You're missing a little thing.
Is there a plus on NH4?
Yep. Don't forget those. Okay. Any questions? Is this the net? Shakes or nods, acceptable. It is the net. Is this a strong base? Because where is the only place strong bases are coming from, and what do they have to have in them? They got to have hydroxide in them, and they got to be from group 1 or 2. That's how we recognize it. Okay? I'm going to skip straight to this. So we're going to do. So those have all been reactions with water. Remember, water can act as either an acid or a base. Now we've got, let's do this. You got 30 seconds. Go. 5 of diamonds.
NaOH plus.
Huh?
Sodium hydroxide.
We have sodium hydroxide over there, though.
Or, sorry, sodium NaOH2 plus.
This is an acid-base reaction hidden in what kind of reaction? Before we started talking about acids and bases. Do you remember what kind of reaction this is? So what is it as a double replacement reaction?
H2O and sodium bromide.
Good job. That's what makes this one a little tricky, because we start getting into a pattern and stuff, and all of a sudden, boom, we got a double replacement reaction. It is an acid-base reaction. What's giving up the hydrogen? What's the acid on the reactant side? The hydrobromic acid. And what kind of acid is it? Strong. And this is a base. We know it because it's what kind of base? Strong base. So this is a double replacement reaction. This is why when I taught you guys how to do double replacement reactions, I said one of the things that might help is if you write the product as HOH. Remember that? Because what's happening? This hydrogen's trading places with the sodium because the hydroxide is accepting that hydrogen. And we make HOH, or water. I don't care how you write it. Just remember that even though we're writing it as HOH, it still doesn't get split apart, right? It's still water. Maybe you got the net on this now?
H plus Br minus plus Na plus OH minus equals H2O plus sodium bromide.
Is sodium bromide soluble or not? By this point, I would think you guys would know rule number 1 well enough to know that it does. It's going to be aqueous.
So plus Na plus and then Br minus.
So that's a complete ionic. Now what can cancel out?
The sodium and bromide.
Which leaves us what for our net now?
H plus OH minus equals H2O.
If you have a strong acid reacting with a strong base, no matter what, okay, that's a lie. There's one exception to this. I'm not going to worry about it. So for everything that you're going to see, okay, for everything that you would be presented with, if you have a strong acid and a strong base, that's your net ionic equation. Has to be. Okay? Questions? Strong acids, strong bases. The strong base is what throws people off because it's an ionic compound. They look like double replacement reactions. Okay? That's an ionic equation. "30 seconds. Give me the net ionic equation." Hannah. Complete this and then give me the net.
H2O. Cl minus. And lithium plus.
Is that the net? What's the net?
H plus. Is that not it?
Keep going.
Cl3 minus. Lithium plus. OH minus. H2O. Cl3 minus. Water plus.
Okay. So this does not get split. Can you tell me why? It is. And again, you wouldn't know because you don't have those 6 memorized because you weren't here when I told you to. But I just told you it's not going to split, which means it has to be a weak. Okay? So, if we keep this together, this would be the complete ionic. What can cancel? So the net ionic equation for this is just what's left over. Are we okay? Questions? So we're still doing the same thing, right? We just got to be careful about what we split apart and what we don't. Any questions? Yes.
Why is lithium and water not put together?
Why is it split apart?
Yeah.
Rule number 1. Group 1 metal soluble.
Like in the first equation.
Oh, this one?
Yeah.
It is split apart here.
On the other side. Why are they not put together?
Oh, because that's what Hannah told me. And I think, Hannah, when you did that, you thought this was going to be the net equation, didn't you? So she was kind of in between. She knew what the products were going to be, but didn't realize that these needed to be split apart. This didn't. Okay. So thanks for pointing that out. I will change this. So if you were just writing out the general equation, that's what it would look like at the beginning. Before you do anything to get to the net ionic equation. Okay. Other questions? Okay. And that's what the homework was based on. Now, this slide is just basically a straight up definition thing. Amphiprotic simply means that you can have something act as an acid or base. Acid or base. So, water we've seen can act as an acid or a base. That means it's amphiprotic. Ampha, amphibian, this prefix can be both ways. Okay? Or I don't know what the real definition is, but if you think of an amphibian, it starts off in water, ends up on land, right? It can go in both places. Usually an anion. So these are anions, remember they're negatively charged, that has a hydrogen in the formula. So this could give up the hydrogen or it could take a hydrogen. Ammonia could be an acid. It's very rare, though, that it would act as an acid. Most of the time, we're going to see ammonia as a base. I'm not saying it's not possible. I'm just saying it's not common for it to act as an acid. Okay, so I alluded to this in lecture last time, that acid-base chemistry is really just the chemistry of water. And to really do this justice, we would need another probably 2-3 weeks of school. We don't have that. So we're going to kind of condense things a little bit. So last time in class, we talked about reactions going both directions, correct? So when we have weak acids and bases involved, they can split apart, but they don't all the way. That's the back and forth thing. In water, water on its own has what we call an equilibrium reaction. So if I had pure water, this is the reaction that's going to be taking place in water. A water molecule is going to act as an acid. So we said that this, right here, this water, say it's going to act as the acid, and this is acting as the base, then we see that this is going to be giving up a hydrogen. That would leave us with the hydroxide. This is going to accept the hydrogen. That would leave us with the hydronium. This is taking place constantly in pure water, or any water. We have an equation that tells us the amounts of these two things in our solutions. Now, in pure water, if a water molecule acts as an acid and a water molecule acts as a base, for this reaction, we're going to get one of each. Which means that we are going to have equal amounts in pure water. We're going to have equal amounts of hydronium and hydroxide. The amounts of those are determined by this equation right here. So I'm going to show you how this equation can be used here. So if my Kw is equal to 1 times 10 to the negative 14, that's a teeny tiny little number, right? What that's telling us is that the amount that water undergoes this reaction is teeny tiny. But us as biological things, those have large effects. Even though it's teeny tiny amounts, have very, very big effects on us. If that is equal to the concentration of hydronium and hydroxide, bracket means concentration. So if you have something given in brackets, that means what's the concentration? What's the molarity of it? Now, in pure water, the hydronium concentration is going to be what compared to the hydroxide? I just said it. If I have this act as an acid and give a hydrogen up to the water, this water, so this water acts as an acid, this water acts as a base, how many of each of these am I going to get? We get one each. So in pure water, how many of those should we have concentration-wise? Hydronium should be what to the hydroxide? Reacting 1 to 1, so they should be equal. What are the values then of these going to be? If I plug into that equation, say 1 times 10 to the negative 14 is equal to these two multiplied together, but we're looking for them. They're the same value. Mathematically, think algebra now. If they're going to be the same value, let's give them the same variable. What do you want to call? What variable do you want to use? X. You guys are so freaking boring. X times what? No. If they're both the same, we're going to make them X. We're going to have X times, or don't say 2X. Thank you. Math teachers freak out right now if they hear you say 2X. So I got 1 times 10 to the negative 14 equals X squared. I want to know what X is. What do we do? X is going to equal the square root of 1 times 10 to the negative 14. Put your calculators away. You do not need them, or you should not. For crying out loud, your math teachers drilled this into your thick skulls. If I'm taking the square root of an exponent, what are we doing to the exponent? Dividing it by 2. So it's 1 times 10 to the... It's not that hard of math. You just got to remember it, right? So that means in pure water, the hydronium ion concentration is equal to 1 times 10 to the negative 7th. That means the hydroxide ion concentration is equal to what? This makes water neutral. So here's what acid and base chemistry is about. Acid and base chemistry is all about changing these values. In most, not all, in most of the reactions we've seen, water has been involved, right? And we've either had hydroxides or hydronium ions involved. Now, let's go. Does anybody have any questions on what we've got up here? So, if this is a constant, then the product of these two must equal this, correct? What happens if I make this go up then? If the hydronium goes up, what has to happen to hydroxide? It's got to go down. And now we don't have equals, right? It's no longer what? When these two are equal, it's what? It's neutral. If I make this go up and this go down, it's not neutral. It's either going to be acidic or basic. Does anybody know which one it's going to be if this one goes up and this one goes down? So if my H3O, my hydronium ion concentration is greater than my hydroxide ion concentration, non-neutral. What is it? It's acidic. If my hydronium ion concentration is less than the hydroxide ion concentration, now it's easy. What is it? It's basic. And if they are equal, it is what? Neutral. Questions? Okay, pH, pOH. pH and pOH are ways for us to represent the concentration of the hydronium and hydroxides in a different format other than scientific notation. Whenever you see the word just log, what base are we working in? Base 10. That makes sense because scientific notation is based on base 10. Okay? The formula for pH is the negative log of the hydronium ion concentration. It's easy. You hit the negative sign, you hit the log button, and you type your number and enter. That's it. You have the pH. So we're not going to be using logarithms like in math to solve a problem. Are you relieved by that there, Connor? Okay. We're simply using log base 10 as a way of representing numerically the values that are really, really small. Remember, times 10 negative 14 is really small. And when these are equal, we said that they were going to be, the concentration was going to equal 1 times 10 to the negative 7. Right? Are you done, Al?
Yeah, I have one question though.
Okay.
Is it really?
She's not in the screen though. It's all right. So we're going to treat these things as slightly modified. Okay, so neutral. My hydronium ion concentration is 1 times 10 to the negative 7. Find the pH. Use a calculator. Find the pH. And if you need help with this, follow along with Mr. K. Negative sign, log, 1 second EE. Don't do that 10 crap. Second EE, negative 7, enter. Whoa. That's where pH 7 comes from. That's the hydronium ions concentration in a solution. So anytime you've ever seen, you've been told, since elementary school, what's neutral? pH 7. But you're never told what it meant. What it's telling you is how much hydronium ion concentration is in the solution. And all it is the negative log of that value. You used to sit on my desk there. My OH concentration, hydroxide ion concentration, in a neutral solution is 1 times 10 to the negative 7. Do you need to tell me do you need to calculate out what the pOH is going to be? No, because it's the same. If it's neutral, the pH and pOH are going to be the same. Wait for the camera. pH and pOH are going to be the same. pH less than 7, acidic. So we just said earlier that the hydronium ion concentration has to be greater than the hydroxide. Well, why is my pH going down? Let's do this. Let's make this five clubs. Who's 5 clubs? Pick a number between 1 and 6.
4.
So I'm doing this. I'm going to make the hydronium ion concentration greater than the hydroxide. Let's try to do this without having to use a calculator. If I have 1 times 10 to the negative 4th, what is this going to have to be exponent-wise for both of these to multiply together and equal 14? 10. Find the pH of this. So it'd be the negative log 1 times 10 to the negative 4th. Enter. 4. 4. Yeah. As long as it's 1. If there's like 2, 3, 4, anything other than 1, I tell you use your calculator. Okay? Because what does log base 10 mean? It means what value raised to the power of, so 10 raised to what power would give you that number. Okay? So we write this out like this. 0.1, 2, 3. Oops, crap, not 4, 1. This is that number, right? 10 raised to what power would give you that value? Negative 4. So the log of this number is negative 4. What do we do in our equation for logarithms? We change that sign. So we're doing, what's the log of this? Log of this is negative 4. We're changing the sign to make it a positive value. Okay? So, if pH is less than 7, we call it acidic. Why? Because for it to be less than 7, our hydronium ion would have to be less than our hydroxide. If we went the other direction, let's make it easy for us here. If this was 4 and this was 10, so we now have our hydronium less than hydroxide. Going with Ella's pattern, the pH of this would be 10. It's less than a hydroxide, basic. pOH, we're not going to dwell on too much. Yeah, I'm going to have you calculate it, but everything we just said about pH is exactly the same for pOH, except reverse. If I have a pOH below 7, it's basic. If I have a pOH above 7, it's acidic. If I have pOH of 7, it's neutral. Now, for strong acids and strong bases, determining the pH is easy. Because when we have a strong acid or strong base, how do they dissociate? or react with water, however you want to think of it. How much do they do it? They're strong. How much do they react or dissociate? 100%. Okay? So, if I have 0.1 molar HCl, I'm going to have 0.1 molar hydronium. Because it's going to split apart completely or react with water completely. If I have 0.05 molar of nitric acid, I'm going to have 0.05 molar hydronium. I understand that sulfuric acid is the one strong acid that we have that has two hydrogens in it. That is the strong acid I'm going to avoid using, because I told you at the beginning of the year, I'm not going to lie to you, and sulfuric acid works a little differently because it's got two hydrogens. Okay? Again, if we had another 2 or 3 weeks, it'd go into that detail. Hydroxides, though, you have to be careful about. With hydroxides, you can have two hydroxides or ions if it's a group 2 metal. Which means that, so if I had 1.5 molar sodium hydroxide, I'm only going to get one hydroxide, 1.5 molar. But if I had 0.01 molar calcium hydroxide, I'm going to have 0.02 molar hydroxide because I get two hydroxides when it splits apart. Because how much is it going to split apart? All of it. So what would the pH, go ahead and get out your calculators. What is the pH of this going to be? Negative log 0.1. Enter. Who's got it? What's the pH of this going to be? No. No. It doesn't work like that. You can only do it with the, like, if it's 1. So you can have 5 times 10 to the negative 2. Or negative log of 0.05. What do you get? 1 point what? What's the pOH of sodium hydroxide going to be? So, or the hydroxide is going to be negative log of 1.5, and you get what? That is correct. You can have pH and pOH go above 0 or above 14 and below 0. Nature doesn't stop at 1 molar. Okay. What is the pOH of calcium hydroxide going to be? It's 1 point what? 7. All it is, negative log, put the number in, enter. But be aware of what it is that you're calculating. These are hydroxides, these are pOHs. These are hydroniums, these are H plus or pHs. Probably the most useful equation you are going to have is this one right here. Anytime you see the letter P, it means you're taking a negative log of that value. So what I have in the box here is probably the most important equation for you guys to know, so you can go back and forth between pH and pOH. Because if you know the pH, you can know the pOH. So if my pH is 1, the pOH has got to equal what? What's it got to equal? 13. That's all it is. You can go back and forth between pH and pOH easily with that equation. Now, to go from pH, pOH to the concentration, I'm going to just teach you button pushing because I don't want to teach you the algebra again. Okay? So I'm going to flip over to this slide here. You guys are going to look at it, but I'm going to show you on my calculator on the screen, and I'm going to put some questions over on the board. So we've already gone over how to go from pH or pOH from the concentration. It's easy, negative log or whatever. But if you need to know what the concentration is when given the pH or pOH, so I have a pH equal to 3.74. I want to convert that to what is the hydronium ion concentration. Because remember, pH is just a fancy way of saying what's this. On your calculators. Second log. Now remember, we're going out of pH. Remember, we changed the sign to be positive, correct? Or the opposite of what it was. So if I have a value of 3.74, that meant the log of it was negative 3.74. So change the sign, make it negative. If it were negative, make it what? Positive. I'm going to try to stick with just positive values for pH and pOH, just to make life simple. Okay? So we would change the sign, make it negative, and we just type in 3.74, enter. So that's going to be 1.82 times 10 to the negative 4. Is everybody okay with what we just did button pushing was? So if I had a pOH equal to 9.36, and I want to know what is the hydroxide ion concentration, I would type in second log, make sure you're using the base 10, second log, negative sign, 9.36. Enter. Questions? One last thing. You can find the pH or the pOH now for any solution. All you need to know is one thing. So, I'm going to switch back over to the notes. You have a whole set of equations here, right? To choose from. Pick and choose. If you had the hydroxide ion concentration and you wanted to know the hydronium, plug into this equation right there. If you had pH and you needed to know the pOH, plug into this equation right there. Well, let's say I had a pOH equal to 5.26, and I wanted to know what is the concentration of the hydronium. We have different pathways. Probably the easiest would be to do what to this first? We're looking for hydronium. Hydronium is measured by what? pH or pOH? pH. But I've got the pOH. We can do the 14 minus, so pH minus 5.26, and get a pH equal to 8.74. And now what? The hydronium. Remember, I just showed you how guys how to take it out, right? Be equal to 10 to the negative 8.74. And you'll have it. So can somebody tell me what it is? See, I'm not going to do that logarithm in my head.
1.82.
Sorry, Dave. All right, your homework. In drive. Acid-base reactions 2. Acid-base practice, which I'll show you here in a second. And there's going to be a third one I need to put up, dealing with net ionic equations. I do want to show you what they're going to look like. So this one's just 7 reactions. You're going to write them out as they all have a strong base in them except number 7. Ammonia acts as a what for us? A base. Okay. The acid-base practice is relatively straightforward. I want you to fill out the chart. Practice the button pushing. So here I'm giving you the pH. You can find the pH, you can find that hydronium. With the pH, you can find hydroxide. With the pOH, you can find, with the pH, you can find the pOH. With the pH, you can find the hydroxide. Then tell me whether it's an acid or a base.
What's that called?
It's called acid-base practice. The second part of it, the user not there? It's there. So you're going to complete the worksheet. I have the answers here. I hope you guys understand it doesn't help you guys out just to look at the answers, right? So I would suggest do 3 or 4, then go check your answers. Or do a line, check them. Do a line, check it. Okay? I want you to have the answers so you're not flying blind.